So that's the comparison I want to draw. That Biot-Savart's law, once you compare it to Coulomb's law, you can see the parts of it that actually make a lot of sense, and that'll help us focus on the parts that are complicated and take a lot more mental effort to make sense. So let me write down Coulomb's law. Coulomb's law says that electric field due to a point charge is given by 1 over 4 pi epsilon naught times the charge of the point charge divided by the distance squared. It's what we call inverse square law. And it's a vector quantity. So there's a r hat unit vector that we need. Good? Everyone feels familiar with Coulomb's law, how we defined it? Let me draw the diagram. So if I have a charge Q here, then imagine I'm interested in electric field at this point in space. Then the way, I guess the only thing I had to take care to define is R. So the R is defined in this way. This R is the distance from the point charge to the point in space. And R hat, it's the unit vector pointing from the charge to the point in space. So let's start off with the R. The way we define R and R hat, does it sound similar in both of the two cases? Right? Yeah, in fact, that's how we always define R. So I want you to look at that part. So this R squared part is the part that both of laws have. Biot-Savart's law, at a first glance, it doesn't look like an inverse square law. And in fact, many of the formulas that we will derive, it won't look like magnetic field is going as 1 over R squared. But the very basic underlying law is still inverse square law. That's what this 1 over R squared tells you. And all right, so that's one. That's actually the biggest point of agreement. I guess the other point of agreement is that there's this constant of proportionality. I mean, they both have to. They both have this weird 4 pi for some reason. If you remember back to electricity, the reason they said 4 pi was so that we can make the Gauss's law simple. It's a similar reason that this has 4 pi here. This is going to make Ampere's law, which we'll cover next Monday. This will make Ampere's law simple. Yeah? And the constant, for some reason, I don't really have a good explanation why epsilon naught is on the denominator and mu naught is in the numerator. Somebody decided that was best. Who knows? So these parts are, the parts I circled, and these are similar between magnetic field, the law for the magnetic field and law for electric field. The parts that deserves more attention are these. So with the electric field, I just provided that it's a point charge, I simply gave the whole electric field. But with the magnet, and I could do that for electric field. I mean, I guess if I wanted to, I could say small contribution to electric field due to a small amount of charges but for a point charge, I didn't feel that that complication was useful, so I didn't do that. But with the magnetic field, I'm not doing that. I'm starting right away from description of a small contribution to the magnetic field. Why? Is there no such thing as point current? Yeah, there is no such thing as point current. Like if you're going to have a current of any kind, you are going to have charges that's flowing from one point in space to another point in space. There's no such thing as point current. In fact, in most cases, if you have a current, normally it'll have to make some kind of loop so that you have an electric circuit. Or you might have something that's infinitely long so that you don't know where it begins or where it ends. If you have just a segment of wire that where you know where it starts and where it ends, then you cannot have current here without accumulating charges somewhere. And I mentioned a couple of times how difficult it is to accumulate charge. Good. So that's the beginning point, that when we discuss magnetic field, the various basic element that's generating magnetic field is current. But you cannot talk about point current. There's no such thing as current at a point. You have to always talk about current over a length of wire, which is why we are forced to describe things this way. So we have a small section of wire, or small section of current carrying wire that's providing a small amount of magnetic field. And even for the simplest example we'll work out today, that would be circular loop of current. We are going to have to do an integral of some sort. So that's one thing that makes magnetic field difficult. The second thing is this. I mean, there's really no way getting around it. And that's why we spent some time going over cross product, even though you were supposed to know about cross product before coming into. But the reason spending time on that was worth it was that the direction of magnetic field, it's described through this cross product of two vectors. And that's why you had to be familiar. You had to have enough practice with cross product so that you won't make mistakes when you figure this out. So that's the comparison with electric field. So there are parts of it that are very similar, and we don't have to worry about it. Like, all right, that looks like what we have seen. And there's part of it that's nothing like what you have seen before. So you need to give yourself time to get used to it. So let's use these diagrams to illustrate the direction of the electric field and the small contribution to the magnetic field using the vectors that are drawn there. The electric field is the easy one. It says the direction of electric field will be in the same direction as the r hat vector, right? There's no other vectors here. So direction of electric field due to this point charge points this way. Anybody here surprised by that? All right, I mean, that's the simple one. We didn't, in fact, spend any time going over this when we did the electricity because it's simple, intuitive. You don't need me telling you a bunch of stuff. It's the magnetic field that'll take more effort. So let's do that. So as long as you focus on this part that I boxed, there's no other vectors here. We are not describing current as a vector. The sense of the direction, we put all of that on the DL. So current is not a vector. In fact, it doesn't even have a sign. The current is supposed to be just a positive number that's telling you how much current is flowing. All the sense of direction is placed on DL. And all these are magnitudes and constants. So whatever direction this DL cross r hat points in is the direction the contribution to the magnetic field will point in. So when you look at this here, all right, so DL, I guess I should draw it maybe bigger so that, let me actually take this DL and transpose it and draw it here so that I can have something to visually see. So this will be my DL, at least the direction-wise. Good. This is the same vector I had here, just drawn super tiny before. Okay. R hat vector, let me take this R hat, translate it, draw it here. So this is the direction of R hat. All right, now I have something to look at, apply my right-hand rule to figure out what the direction of DL cross R hat is. What's the direction of DL cross R hat? Yeah, into the board. So the contribution due to this little segment of wire to the magnetic field here is into the board. Let me draw R hat here. So this is the direction of my magnetic field. Does that make sense? So let me do two more things here. So what we have done so far is figure out the contribution to the magnetic field at this point due to this small segment, which means to have a sense of the overall direction of the magnetic field, not just the dB, but I want to figure out the direction of the total magnetic field, What would I get if I add up all the contribution from nearby currents? So that's what I want you to imagine. For this straight wire, as I look at different parts of the different segments of the wire, which of these two vectors are changing? DL or R hat? R hat is changing, right? All right, so let's do a couple more points so that I have some sense of, is this dB continuing to point in the same direction, or is it going to start pointing in some different direction? So let's call this point 1, this is point 2, and call this point 3. So for these three different points, for point 2, point 2, so this is going to be my vector R hat, 2. For point 3, this is going to be my vector R hat 3. So I want you guys to do this exercise in the 30 seconds or so. So what is the direction of the cross product DL cross R hat 2? And what is the direction of the cross product DL cross R hat 3? You might need to use your hand, unless you have the answer already. All right, so what is the DL cross R hat 2? Yeah, still into. So, R hat 2, it's like this vector except over this way. So DL cross R hat 2 is still into the board. And what about DL cross R hat 3? Yeah, still into the board. So the angle between these two are changing, but overall sense of the direction isn't changed. So angle between them are changing, so the magnitude of the cross product might be changing, but the direction of it's not changing. So when you add it all up, this direction is going to end up being the direction of the overall magnetic field. So at this particular point in space, magnetic field is pointing into the board. And if you try this exercise with any of the other points on this side of the wire, you'll get the same answer. Magnetic field is pointing into the board. So, all right, let's do one more point just to confirm some geometric picture that you might have already. So let's pick a point here, up here. So I want to figure out what is the direction of magnetic field at this point. So you can do contribution from 1, 2, 3. Let me just do the contribution from 2 as an example. So the DL vector still doesn't change. That's sort of determined at the source. So the R hat 2 vector, because the point that I'm looking at is now different, this is going to be my R hat 2 vector. What's the direction of the magnetic field at this point? Yeah, DL cross R hat, it's out of the board. And when you try similar exercise with all the other points, so for every single point on this side of the board, you'll get, well, it's out of the board. So, all right, so that's sort of the picture you get when you imagine individual points